Part G, the last topic of Module 4. Yeah. So after lecture today, so we will finish Module 4. And after today's lecture, I need to give you homework assignment number 2. Yeah. So next week we will start our last module, Module 5. Module 5, our last module. Yeah. And we want to finish Module 5 in 1 week. Yeah. 1 week. Then we need to prepare for the final. Yeah. All right. Quicksort. Yeah. First, introduction to Quicksort. Yeah. So this is our sorting algorithm number 5, the 5th we learned. Yeah. So we have learned selection sort, bubble sort, insertion sort, merge sort. Now, number 5, quicksort. Yeah. The question, why we need to learn another new sorting algorithm? Yeah. So there is some reason. Yeah. All right. So because for this class we plan to learn a total 7 sorting algorithms. And you can see for the same sorting problem, we learn total 7 sorts in different ideas, methods. And you can see these sorts have different properties. So in the real world applications, in different situations, we may like to select different sorts. All right, so here the quicksort, from the name, you can see this sort should perform better than other sorts. Because they use this word quick. Yeah. Actually, it is. Yeah. This sort has best. Yeah. Best. Yeah. Average case efficiency. Yeah. So when we do experiments, when we run many sorts, we apply them on the same set of data. Yeah. So then we look at the response time. So we run many times experiments. At the end, you will see this one performs the best. That means it has the best overall efficiency or average case efficiency. May not be the best, worst case, best case, but best average case efficiency. So that is important, because in the real world situation, when we choose a sort, we like to pick the one with best overall efficiency, the best average case efficiency. All right. So now let's look at the main idea. How can you get the best overall efficiency, right? Yeah. Yeah, so here, for this one, we emphasize overall performance. But before we do experiments, we don't know. So we just try to, develop different sorts. So at the beginning, so people just develop many different sorts. So then they run experiments on all of them and see which one performs the best. So then pick the best one. All right, So the same sort problem, and this time we use the divide and conquer approach. Yeah. But when we apply divide and conquer approach, we may change our focus, right? Yeah. Every time when we apply divide and conquer, we can use different ideas, different views, different understanding, and set different focuses. Yeah. So here we change the way we apply divide and conquer. Yeah. So the goal, make the overall performance as fast as possible. Yeah. But when we design this sort, yeah, how do you target the overall efficiency, right? Yeah. Yeah. So here we just want to use a completely new idea, yeah, comparing with what we have done so far. This time we want to apply a completely new, different way using divide and conquer. Yeah. We can tolerate poor worst case performance. Yeah. So we do not try to avoid poor worst case performance. We allow poor worst case performance. Yeah. So remember last time I mentioned, what's the poor worst case performance? When you have the worst case performance in this category, big theta of n squared, that's poor. Okay, that's poor. All right. Yeah. Not poor if you have big theta n log n. Yeah, that's the good one. Okay. Yeah. If the worst case in this category, we cannot say poor. Okay. Yeah. It's really good. Yeah. That's the best we can get. So we cannot say poor. Okay. Yeah, but n squared, you can say poor. Yeah. Worst case performance. Yeah. So this one we allow poor worst case performance, but we want to make the probability for the worst case should be very low. Yeah. 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 Because our goal, we emphasize overall. What do you mean overall performance? That's the average case. Because only the average case efficiency is the fair measure for the overall performance. Yeah. The best case, the worst case, they are not a fair measure. Okay? So the average case efficiency is the fair measure for the overall performance. Yeah. All right. Now we change the view on divide and conquer. Yeah. Here I want to, let's compare merge sort and this new way applying divide and conquer. Yeah. So this column, we list the merge sort way using the divide and conquer. For the divide and conquer, there are 3 steps. Step 1, divide step. Step 2, conquer step. Step 3, combine step. Yeah. Yeah. And the conquer step, usually we use the recursion. Yeah. Yeah. We implement divide and conquer using recursion, and recursion covers the conquer step. Yeah. So we only need to work on first step, divide, and the third step, combine. Yeah. All right. For the merge sort, let's recall the merge sort. Divide step, we have a original array. We split right in the middle, right? So the merge sort, we split right in the middle. So that split is very easy, very fast, right? You do not need to do much work. You just split in the middle, right in the middle. Yeah. So you look at the indices. Yeah. You find the index of the midpoint, then you get two summaries. That's your split. Yeah. So in that way, the amount of work you need to do is minimum, right? So here we use big theta of 1. That means the minimum amount of work. Yeah. All right. But for the merge sort in the combine step, you need to do a lot of work, right? Yeah. So you need to merge two ordered arrays. The amount of work you need to do, big theta of k. Yeah. So here k, we represent the total number of elements you want to sort in that step, in the current step. Let's say current step. Yeah. Yeah, because when we use the recursion, the current step we call the recursive function, the size of the data is different. Yeah. So here we use k, refer to the total size of data in the current recursive function call. Okay, yeah. So that's the merge sort. But here, for the new idea, we want to change a different way. Yeah, completely different way. Yeah. So this time, we want to make our combine step. When we get two ordered arrays, we want to put them together to form a new larger ordered array. We want to make that step minimum amount of work, minimum. Yeah. So that step, we want to use big theta of 1 amount of work. Yeah. Yeah. How can we do that? Yeah. So this is our goal. Okay, this is our goal. We want to, yeah. So here we want to do in a different way, completely different way. Yeah. Otherwise, if you do the similar way as the merge sort, you will get the similar sort. Yeah. So we want to get a completely different sort. Yeah. So here, that step, big theta of 1. But think about if. So here it's a trade-off issue. In the first step and the third step, there is a trade-off issue. If you put a minimum amount of work in one of the two steps, you have to do a lot of work in the other step, right? Yeah. It's impossible. Both steps, you do minimum amount of work, right? Yeah, it's impossible because we know sorting as a whole task, it should take a large amount of work. Yeah. Yeah. So, especially, think about, especially based on what we learned in the last lecture. Remember last lecture, the lower bound. That's what we learned the last lecture. The lower bound of the comparison sort, that is this amount of work. N factorial. Yeah. And this, yeah, some of you may ask, what is this function, right? The ceiling function of log base 2 of n factorial. Yeah. So we derived this formula. But many of you may not be able to see what is this function. Yeah, because it looks too complicated. So we see n factorial. Yeah. And it's hard to estimate how large is the n factorial, right? How large is the n factorial? Hard to estimate. Yeah. So here I can give you approximation So that complicated function can be approximated by n log n. This way we can see much better, right? N log n. Yeah. N log n is very close to log of n factorial. Yeah, n log n. Yeah. N log n. Yeah. So if you want to estimate this function log base 2 of, so you can get some constant times n log n. Yeah. Certain constant times n log n. Yeah. Yeah. And there is a calculus method we can use to do estimate. Yeah. So we can use integral. Yeah. We can estimate the area using integral to estimate the area. So then we can calculate the value of this function, yeah, to get a very good estimation. Yeah. Here I skip the detail, yeah, estimation detail. Yeah. Yeah. So you just know, this function, close to log of n factorial. Yeah. Probably there is a constant associated. So if you compare the two functions not quite the same, so you need to think about some constant c. Yeah. Yeah. When you do comparison, it's better to look at the n relatively large. Then you do comparison. Then probably there is some constant c, yeah, between them. Yeah. All right, so now this tells us when we sort any given n element array, this amount of work, we expect to do this amount of work, right? Yeah. Yeah. So that means if you do very little amount of work here, you have to do a lot of work here. Okay? Yeah. You have to do a lot of work in the first step. Yeah. Yeah. So here let's try. Our main focus is on the divide step. Yeah. In other words, we can say it this way. We are willing to do more work in the divide step. Yeah. As a result, we want to make our combined step minimum amount of work. Yeah. The amount of work we put in the combined step, the minimum. That's our design goal. Yeah. All right. How to achieve this design goal? Yeah. So let's look at the slide, next few slides. Yeah. Yeah. All right. Yeah. So the quicksort idea. Yeah. This is the quicksort idea. Yeah. How to make combined step easy. Yeah. Yeah. So when we start, we want to think about, yeah, we want to imagine under what situation we can make the combined step as easy as possible. Yeah. All right. Yeah. So here, the idea is very smart. Yeah. All right. Yeah. So let me open the chat area. So if any of you type chat message, I can see. Yeah. All right. Yeah. My second computer. Yeah. All right. Yeah. Yeah. Try to follow. Yeah. So this here the idea is not very hard, pretty simple. Yeah, but very smart. Yeah. Almost do nothing. Imagine. What do you mean? You can do almost nothing in the combined step. you have two ordered arrays. You put them together without doing any comparison, you can get a whole ordered array. Can you imagine that situation? Yeah. Remember, in the last lecture, when we learned the merge sort, we have a merge step. If we want to merge two ordered arrays, we have two formulas, right? The worst case, so for the merge sort, let's recall, for the merge sort, we have two cases. Worst case formula and the best case formula. All right. Worst case formula, m plus n minus 1. Two ordered arrays. One has m elements. The second one has n elements. The worst case, you need to do this many comparisons. M plus n minus 1. Here, the best case, you need to do the minimum of m and n, this many comparisons. So that's for the merge operation for any given two ordered arrays. But here in our Quicksort, we have two special ordered arrays. It's not any given two ordered array. So we have here, because we do the combine step after we do divide step, conquer step, then combine step, right? Combine is step number 3. So first, in the divide step, we try to, remember so here, let's recall, in the divide step, first, you need to do a lot of work in the divide step. In the divide step, you need to do this amount of work. That's a lot of work. When you put a lot of work in the divide step, you should get some good property in your data, right? If you put a lot of work, your data after the divide step should have very good property, right? Because that's your investment. After you make this much investment, you want your data with good property. Then it's worth the investment. Good properties. Right? Now, we want to think about what's the good property we want to have after the divide step, so that when we combine, because after the conquer step, the second step, conquer, we call the recursive functions. We get each of the two subarrays ordered. So after the conquer step, you can assume those two subarrays are ordered. So the third step, when we combine two ordered subarrays, these two ordered subarrays should be, so two ordered subarrays, you can assume there are two special ordered subarrays. In what two special ordered subarrays, when you combine them, you just put them together, you get one overall ordered array. Think about that situation, that special data arrangement. Is it possible we can get that kind of special data arrangement? So this is the key point here. So if you can get this point, then so we pretty much halfway. We're pretty much halfway, solving the whole problem. All right. Here, divide step. So a lot of unknowns we need to do in the device step. Yeah. But we like to focus on the nice property we like to have after the device step. How can we combine two ordered arrays to make a larger ordered array without any comparison? Yeah. Here, without any comparison. You put them together, the whole array is ordered automatically, and you do not need to do any comparison. How can that happen? Yeah. All right, yeah. So before conquer, not sorted, each subarray not sorted, but after conquer, they both sorted. So we can assume they both ordered when we combine them. Yeah. All right. So when we combine them, the easiest way to combine two ordered arrays, put them together without any comparison. Yeah. So that's what we want to have. Yeah. This property. Yeah. So this is a nice property. Yeah. This property we want to achieve from the device step. Yeah. All right. Yeah. The whole array is automatically sorted without any comparison. You don't need to do any work. Yeah. You just put them together. Yeah. All right. Yeah. So here you compare with the merge sort. Merge sort, we need to do a lot of work here. Yeah. Here, almost nothing. Yeah. So that's what we mean. What do you mean almost nothing? This is the meaning of almost do nothing. Yeah. All right. Yeah. So after the conquer, when combine, do nothing. Yeah. The question, what's the property? Yeah. Yeah. You have to, you can make some brave assumption here. Yeah. You need to understand your data. Yeah. What property of your data you want to assume after the device step. Yeah. Yeah. So that's here. Think about this is the main property. Yeah. This means any element in the first subarray should be less than or equal to any element in the second subarray. That's the main property. That's the main property. Okay? Or you can understand this way. The maximum of the first subarray is less than or equal to the minimum of the second subarray. Yeah. You can make this, very brave assumption. Yeah. Yeah. In your imagination, you can make this brave assumption, but after you make this property as your goal, you need to achieve this goal in the device step. You need to make it. When you split your data into two subarrays, you need to make this property happen. Okay? Make it happen. Yeah. All right. So if you have this property, now think about if A subarray is ordered, B subarray is ordered, you put them together, the whole array is ordered, right? Without any comparison. Yeah. Because the maximum element of A subarray is less than or equal to the minimum of the B subarray. Yeah. So you put them together, all the elements are in place. Yeah. Automatically. Okay? Yeah? So that's the nice property we want to have. Yeah. All right. So our next step, device step. After we set our goal, set our main design goal. This is our main design goal. So we need to implement our device step to achieve this goal. All right. So the most important step in the quicksort, the device step. Requirement, of this divide step. How to split the array into two subarrays, A subarray and a B subarray, such that the value of any element in A subarray is less than or equal to the value of any element in B subarray. Yeah. All right. Yeah, but after the divide step, we do not require A subarray is ordered, B subarray is ordered. We do not require that. Okay? And usually they are not ordered. So the A subarray, B subarray, you in general, they are not ordered. Yeah. But they have the property, the maximum element in A subarray is less than or equal to the minimum element of the B subarray. And then in the conquer step, we call our recursive functions on these two subarrays to get them ordered. So that's the conquer step. Then after that, we combine them. Yeah. All right. Next topic, G.2, partitioning in Quicksort. Yeah. That divide step, we need to implement the details, and we call it a partitioning step. Yeah. So let's look at the detail of the partitioning step. Yeah. All right. Yeah. The goal is this one. Yeah. Yeah. These two inequalities equivalent. Yeah. Equivalent. The first inequality you need to understand as any element in A subarray. Yeah. So you can choose the maximum. Yeah. You can choose any element. Yeah. But the best you can choose as the representative, you want to choose the maximum of the A subarray. Yeah. Then, when you choose any element in B subarray, the best representative you want to choose in B subarray is the minimum of the B subarray. Okay? So there you get a second inequality. So, yeah. These two inequalities should be equivalent. All right, so now let us fix the implementation details. So this is another challenging and interesting, smart step. The implementation details are very smart. Yeah. So let's look at the basic idea here. Here, let's consider the original array. So this diagram means the original array, it's not ordered. Yeah. This capital A array not ordered. Okay, yeah. All right. The question, how can we split this array into two parts? Yeah. Left subarray and right subarray, such that these two subarrays have this property. That's not easy, right? That's not easy. Yeah. All right. Yeah. So here, the first question you may like to ask yourself, is it possible? Is it possible to split the given array into two parts such that the left subarray, the maximum value of the left subarray is greater or equal to the minimum value of the right subarray? Is it possible? Yeah. First thing, you may ask yourself if it is possible, right? Yeah. So here, in order to answer the question, if it is possible, I need to give you the clear meaning of split. What do you mean split, right? Yeah. What's the exact meaning of split in this situation? Because when we understand this word, the meaning of the split, this word, it could be very vague, right? The split, its meaning, definition may not be very clearly defined, right? All right. So here I want to give you more important information about the split. When you split your data, you're allowed to move the elements in the given array. You're allowed to move the elements around. That's the meaning of the split here, okay? Because we are allowed to move elements around within the given array. Because if you are not allowed to move elements around, then it may not be possible, right? It may not be possible you can split the given array into two subarrays such that the maximum of the first subarray is smaller, less than or equal to the minimum of the second subarray. It may not be possible, but if you are allowed to move the elements around, so any way you want to move, you're allowed to move, okay? So let's say, what do you mean, move? You can swap any two elements in a given array. Swap. So let's consider the swap operation. You can swap any two elements as you like. Then it is possible, right? After certain number of swap operations, you can get two subarray, left subarray and the right subarray, such that the maximum of the left subarray is less than or equal to the minimum of the right subarray. Swap operations. How to use swap operation in a well-organized way. Okay? It's not a random way, right? If you just apply the swap operations in a random way, you cannot make that happen. Okay? So you have to apply the swap operations in a well-organized way. Then you can achieve that design goal. So this property is our design goal. All right. How to split into two subarrays. So here you can see when I draw the general two subarrays, I cannot assume these two subarrays have the equal size. No, you cannot assume. Not like a merge sort. Merge sort, when we do the split, we can assume, because we always split in the middle. We split our data right in the middle. Here you cannot assume. Here, these two subarrays in general, they have different data sizes. All right. So the only property we want to have this inequality as the property after we split it. All right. Here there is an uncertainty regarding the sizes of A subarray and B subarray. Nobody knows the data sizes for A subarray and B subarray. So that's uncertainty, right? Uncertain. It is uncertain. How large is the A subarray? How large is the B subarray? Uncertain. Okay? How to make it certain? The next question. How to make it certain? Or how to determine the sizes of A subarray and B subarray? How to determine their sizes? Make it certain. Then the next step, in order to determine the sizes of two subarrays, we need to introduce a special element. That element can separate two subarrays. That special element is very important. Yeah. We want some special element between these two subarrays to tell us what is the left subarray and what is the right subarray. Okay, the element, that special element should be located between these two subarrays. Then all the elements at the left-hand side of this special element we treat it as the left subarray, and all the elements at the right-hand side of this special element we treat it as the right subarray. All right, the question, swap, Elroy question, swap between the two subarray or within. Oh yeah, all right, yeah. So Elroy asked a question, some subtle point. Yeah, so let me answer within the original array. Yeah. The answer to Elroy's question is within the original array, not between two subarrays. Why? Because at that time, when we do the swap operations, those two subarrays are unknown. Uncertain. We don't know. At that time, we don't know what are exactly those two subarrays. Nobody knows that. Okay? Only at the end we know. Okay? Only when we finish the partitioning step, then we know those two subarrays. In the middle, we don't know. In the middle, still a lot of things uncertain. So when we swap operations, when we swap two elements, so we need to have a good control on those two elements. Where do we swap? Okay? When we swap two elements, we should put them under control. All right, good. So here. So you can see, that's why I said before, this step is very smart. Okay? So we can do all these things in a well-controlled way. Okay? Yeah. All right, so let's continue the story. So here I want to emphasize this special element is extremely important because we use it as the separator of two subarrays. Very important. So we want to give a special name to it. Special name, special concept for this very important separator element. And you can see this special element has key property. It must be in place, right? Its location, it must be in the right place when the whole array is sorted. That's the key property of this element. Then all the elements at the right hand side of this one, they should have the values less than or equal to this special element, the value of this special element. And all the elements at the right hand side of this special element should be greater than the value of the separator in place element. All right. And we use this, element to mark the boundary of the two subarrays. The boundary. Okay? But we need to determine the boundary. So you need some smart idea to do it. All right. Here, look at this diagram. This diagram, I put a special element between A subarray and a B subarray, I insert a new special, very important separator element. I use P. Here we introduce a concept called a pivot element. This element we call it pivot element. Okay, so we use P. Yeah. The pivot element, it is in place first. Then all the elements after the swap operation, remember we are allowed to use swap operations. After so many swap operations, we want to make sure all the elements at the left-hand side of this pivot element, their values should be less than or equal to P value. Okay, pivot element, it has a value. And all the elements at the right-hand side of this P should be greater or equal to P. If we can get this property, then we achieve our design goal, right? So remember our design goal here. Our design goal, if we can achieve this state, we can get our design goal. Yeah. All right. The next question. So here we can see our picture better and better, but we still lot of details remain, right? Yeah, still we need to fix a lot of details. Yeah. But we can see our picture better and better. Yeah. All right, so next, we want to see how to make that happen. Yeah. That pivot element looks like magic, right? How can you find that pivot element? That magic pivot element. Yeah. But so a really smart idea, so I don't know who is the inventor of this algorithm, so very smart idea, not very complicated. It's simple, but it solves the problem in a simple way. Here, because when we are given an arbitrary array, we have no idea on the values on the elements in the array, right? You don't know which element is the largest, which element is the smallest, which element is the median. You have no idea on that kind of detailed informations in the given array. Nobody knows, right? So you cannot assume any information about the values of your given elements. So in that assumption, which element should be used as the pivot element, right? So first you need to answer this question. What element should be used as the pivot element? Because you need to choose one of the n elements as the pivot element, right? But which one is the best choice, right? Which one is the best choice? Here. So let me throw in a question. Let me throw in a question here. Question. Do you think is the median, the median of the array, right? Is the median a good choice for the pivot? Think about this question. Is the median element a good choice for the pivot here? Right. Think about it. Do you want to select the median and use it as the pivot to separate the two subarrays? That's the question. All right? Yeah. Let me tell you the answer. The answer is no. The answer is no. Why? Answer is why median is not a good choice. Because let me write it. Because it is too costly to use the median. As the pivot. Okay? How to find the median? Right? Do you know how to find the median? Yeah. There is some algorithm to find the median, right? Yeah. So later, after I finish this Quicksort, if I still have some time, I estimate I may have half an hour time. I will talk about how to find the median in general. Okay? Yeah. But the algorithm to find a median is very expensive. You need a lot of comparisons. You need a large number of comparisons to find the median, and it's not worth it. We don't want to use that many number of comparisons to find the median and use it as the pivot. Too expensive. Now, if you want to use the median, real median as the pivot, your algorithm will be very, very slow. Okay? Yeah. Even much slower than the merge sort. Okay. If in that way we just use the merge sort, we can do much better. Yeah. So you cannot do the median. All right? In this step. Yeah. Forget about the median. Yeah. All right. So then the question, which element should we use as the pivot? Which element should we use? We do not want to use a lot of comparisons to get the pivot. Okay? Yeah. So here the answer is we select a random element as the pivot. A random element. Okay? Randomly selected element. Yeah, because no specific information about the values for the given elements are known. If not known, then any element is equally good to be the pivot element. Any element where it is used as the pivot element, the result is equally good by the probability. Based on the probability, the result is equally good in the probability sense. Okay, in the probability sense. So based on this understanding, we just randomly select any element and use it as the pivot. So we finished this step. We answered this question, how to select a pivot. No reason to favor any particular element, right? You don't know which element is better, which element is worse. You have no idea on it. If you have no idea on it, then just select anyone in the given array. Okay? Yeah. Could be a random selection. Yeah. So let's just do the random selection. Right? Yeah. All right. Position-wise, so if you look at the values of the elements, then randomly selected element, so because when we talk about randomly select element, we look at its value, right? we look at the value of this element. Yeah. Yeah. But there is another important information related to the given elements. That's the positions. Positions in the array. That's another. We know positions are different from the values, right? Yeah. Yeah. The first position of the array, second position, and the last position. Positions and the values, they are not matched at the beginning, right? At the end, they are matched, right? At the end, all the elements are in place. Then the first position corresponds to the first smallest element and so on. But before you sort it, the positions and the values are not matched. Okay? Yeah, they are different. And here we also need to consider where is the position of the pivot. The element at which position in the array is the most convenient for the pivot element. After we select the pivot element, we need to put it somewhere, right? We need to put it in certain position in the given array. But where do you want to place that pivot element? Yeah, yeah, because the reason I ask you this question, this question is a little deeper than the previous questions, a little deeper, the position of the pivot. Yeah. Because in your implementation, think about what's the main work we need to do in our implementation of this partitioning step. What's the main work? Swap operations, right? Swap operations, that's the main work we need to do in the partition step. Okay? But when you do the swap operations, when you do the swap operations to move elements around, how do you manage the location of the pivot element? How do you manage the location of the pivot element? You randomly select an element to be used as the pivot element. Then its position is very important for your swap operations, right? When you do swap operations, the position of the pivot element is very important when you do the swap operations. Okay? Yeah. So that's the reason we want to determine the position of the pivot element before we do the swap operations. Yeah. Otherwise, we may do too much work. If you, in other words, let me say in this way. In a given array, you have some good location for the pivot element, and you have some bad location for the pivot element. If you use bad location for the pivot element, then you need to do a lot of swap operations. If you select good location for the pivot element, then we can do some easier work for the swap operations. Yeah. All right, so here, let us determine the good locations for the pivot element. Yeah. So here, let me draw this another array diagram here. And we want all these squares represent the locations of the elements. And we want to determine what locations are good locations for the pivot. What locations are bad locations for the pivot? Yeah. All right. Think about it. So here, let's select arbitrary location in the middle of this element. Anyone in the middle. Yeah. Can we use this randomly selected location to store the pivot element? Yeah. If you do it, think about how much work you need to do when you do the swap operation. How much work you need to do because definitely if you random select this one, your pivot element is not in place, right? If you put your pivot element in this location, you do not know if it's in place or not. And in general, it's not in place. Yeah. So this element is not in place. If it's not in place, when you do swap operation, you need to do a lot of work, right? Very messy. Yeah. Think about that. Very messy. Not in place in general. Yeah. So when you manipulate, when we move the elements around, this element sit somewhere in the middle, and you can see its role. It has the role as a roadblock. You need to deal with the difficulty caused by this roadblock. Okay? Yeah. Because this element is not in place. When you move elements from left hand side to right hand side to left hand side, how do you control? Yeah. Or, so not in place means value and the position are not matched. Okay? Here, its value is not equal to its position. Okay, not matched. Value, actually, the value rank. Let's call the rank of the value. Not the value itself. The rank of the value and the position, they are not matched. Okay. Rank 1, 2, 3. Okay, the first largest, second largest, the rank of the value, does not match the position. All right. Then, if you want to move elements from left to right, from right to left, it's very, very hard to control. Yeah, because you select a bad location for the pivot. If you select good position for the pivot, you won't have this problem. You won't have this roadblock problem. So think about what are the good locations for the pivot element so that we can avoid this roadblock problem. So they do not. So the element should not sit somewhere in the middle of the array. Yeah. They should be at the end points. Endpoint locations. 2 endpoint locations. They are good locations. Only these two. Yeah, first or third quartile. First element and the last element. Okay? Right here. First element, not quartile. Your quarter, so first quarter, right? First quarter, second quarter, third quarter. So the answer should be first element and the last element. Not anywhere, other than the first and the last. Because only the 2 endpoints. If you put the pivot elements in one of the 2 positions of these 2 endpoints, it won't block any elements swapping, right? When you swap 2 elements, you do not need to consider these 2 endpoint locations because you do not need to touch these 2 endpoints, right? You do not need to touch these 2 endpoints. So you won't have the difficulty caused by the roadblock. There is no roadblock. Okay, you push the roadblock to the 2 ends, so then the 2 end elements, they won't block anything, right? They won't block anything. So the best positions for the pivot element to one of the 2 endpoints. One of the two endpoints. Just select anyone. Okay? Yeah. They are the same. Yeah. They are the same. Okay? Yeah. So the value-wise, no difference, but the position-wise, we want to put it in one of the two endpoints. Yeah. Here, I use the right endpoint. Yeah. So in our textbook and all other places, it may use the left endpoint. Yeah. But the result is the same. Yeah. Some books use the right endpoint. Some places, algorithm implementations, use the left endpoint. Yeah. All right. So here we assume we place the pivot element at the right endpoint. Then our goal after that, we want to put all the elements that are less than or equal to P in the A subarray, and all the elements that are greater than P in the right subarray. Now think about the picture. Now think about at this point, how well can you see the whole picture? Yeah. So this is our current diagram. We have this situation. Yeah. After you see this diagram, can you envision the implementation? How to make this happen? Do you feel it's doable to make this situation happen? Yeah. So let me check the time we have. Oh, we are near the break time, right? Yeah. We are near the break time. Yeah. So let me see how much we need to do next. Yeah. All right. Yeah. The property. Yeah. Yeah. Next, G.3 implementation in partitioning, the detailed implementation. Yeah. Let me leave this part to after the break.